Well, I'm talking about basic research and a moral dilemma. To talk to this academy about basic research is, as we say, preaching to the choir. I think most people, is this working all right? Yeah. I think most people feel favorably towards basic research, and I do. Nonetheless, I would like to make some comments which I hope may be of some use. I'd like to start with a rather poetic quote about the nature of science. The history of the living world is an elaboration of ever more perfect eyes in a cosmos in which there is always something new to be seen. This is by Teilhard de Chardin. Teilhard was a paleontologist, geologist, philosopher, and Jesuit priest. His epigram provides a stunning description of the evolution of science, in which ever more perfect eyes could range from primitive telescopes at the dawn of the 17th century to the giant radio telescope the size of the Earth that is attempting to image the tiny black hole at the very center of our galaxy. I would like to discuss issues related to basic research in the physical sciences and to the central concern of this session of the Pontifical Academy of Sciences. By basic research, I mean research motivated by the joy in understanding nature in contrast to solving a particular problem. It's the conventional description. When Teilhard talked about ever more perfect eyes and a cosmos in which there is always something new to be seen, he was talking about basic research. Einstein's search for a theory of gravity, his general theory of relativity, is an iconic example of basic research. The problem he struggled to solve, to create a theory of gravity that avoided some inconsistencies in Newton's theory of gravity, worried hardly anyone and had no conceivable use, at least not at that time. A startling consequence of Einstein's theory is that gravity affects time. A clock on top of a mountain runs faster than an identical clock at sea level, but not by much. A clock on the peak of Mount Everest should run fast by a few millionths of a second a month. The quest to observe Einstein's prediction for the effect of gravity on the rate of a clock has a well-documented starting date. It was January 11th, 1944. That day, a New York Times article carried the headline, "Cosmic Pendulum for Clock Planned." It was a report of a speech at an American Physical Society meeting in New York City by I.I. Rabi, a physicist at Columbia University. Rabi proposed creating a clock whose ticks were governed not by the swing of a pendulum, but by pulsations within an atom that could be measured by a technique he had invented, molecular beam magnetic resonance. The accuracy of such an atomic clock could be fabulously high. The New York Times article reported that, quote, Professor Rabi said he would like to see someone build an atomic clock that would be capable of providing for the first time a terrestrial check on the Einstein postulate that the gravitational field produces a change in the frequency of radiation. The creation of atomic clocks sprung directly from the quest to see whether gravity affects the rate of a clock. That is, whether gravity affects time. Lacking any other conceivable application for such an accurate clock, the quest provides a clear example of basic research. Nobody rushed to build an atomic clock following Rabi's talk in 1944. The research establishment was in disarray from World War II when there was a technical barrier. That barrier was breached in 1949 when Norman Ramsey, a former student of Rabi's who had just joined the physics faculty at Harvard University, proposed a technique with the awkward name of the separated oscillatory field method. Serious work on an atomic clock started then, and in 1954 the first experimental clock was demonstrated in England. It was known as a cesium beam atomic clock. I would like to digress on atomic clocks for a few moments and then get back to the point. In 1955, I went to Cambridge University, England, as an undergraduate with a Fulbright fellowship. My tutor, Kenneth Smith, did something tutors generally did not do at Cambridge in those days. He talked with me about his research. His work centered on studying the properties of atomic nuclei using Rabi's technique. Smith told me about Rabi's proposal to observe the effect of gravity on clocks. I clearly remember being stunned by the idea that gravity affects time, but I could only store the thought in my mind among the clutter of possibly interesting ideas rattling around in my head. In September of '55, I entered graduate school at Harvard University. Ramsey was on the faculty, and the following spring I joined his group. In the fall of 1956, he told me about his idea for the hydrogen maser, a frequency standard fundamentally different from the cesium frequency standard, but which had some potential advantages. I jumped at the opportunity. When Rabi proposed that somebody ought to build a clock, he was referring to the cesium beam clock. This has been the standard type of atomic clock ever since the idea of atomic clock had been conceived. The first cesium clock was demonstrated in '56, and within a few years, a practical device had been produced. The hydrogen maser is comparable in accuracy to the cesium beam clock, and most time standard laboratories have one or more. Although the hydrogen maser was created specifically to verify Einstein's conjecture about time and gravity, its unanticipated applications are noteworthy. The hydrogen maser made the radio astronomy technique known as very long baseline interferometry, VLBI, possible. VLBI allows astronomers to make radio telescope antennas that are effectively the size of the Earth. It is the technique being used to image the black hole at the center of our galaxy. VLBI enables astronomers to create maps of hydrogen in the universe with astonishing detail, and allowing them to look further back in time than by any other technique. One can hardly think of a better example of Teilhard's concept of ever more perfect eyes. The greatest impact from the development of atomic clocks, however, is the creation of the Global Positioning System, GPS. The GPS is a technical marvel of the space age. It is fundamentally a timing system, and atomic clocks are at its heart. General relativity is also at its heart. GPS would not work if Einstein's theory of gravity were ignored. To my knowledge, nobody had thought about such a system before atomic clocks became a reality, and nobody could have imagined the powers of today's GPS. Today, GPS is ubiquitous. It is at the heart of the air control systems that guide planes in flight and the navigational systems in smartphones and automobiles. The GPS keeps our communication networks and power grids synchronized. It is crucial for medical emergencies. Above all, the GPS is crucial for understanding the existential threat to humanity that is the focus of this plenary session, climate change. Understanding the global climate requires data on a vast number of variables: radiant energy flow to and from the Earth, vertical and horizontal temperature profiles, cloud covering and temperature, sea and land surface profiles, ocean surface temperature and wind speed, global precipitation, water content of the atmosphere and troposphere. The list goes on, and the data are enormous. The primary source of data on Earth's climate is a fleet of 8 weather satellites in polar orbits, 4 from the US and 4 from the European Space Agency. This fleet scans the entire surface of the Earth 4 times a day. Often, the satellites work together in pairs, exchanging radar and LIDAR, that's light radar, signals to look through the troposphere to measure its water content. That particular measurement is crucial to a global analysis because most of the atmospheric water is stored in the troposphere. In addition to the polar fleet of weather observatories, there are clusters of synchronous satellites from various nations that continuously view Earth and particular areas on the Earth. The US has 2 clusters viewing the entire country, one to the points east and others extending to points west. Because hardly any of these global climate measurements would have been possible without GPS, it is valuable to keep the origin of the GPS in mind: mere curiosity about general relativity. Basic research was the driving force for the GPS, and basic research is often the driving force for transformational advances, advances that broadly affect society. Here are two other examples of transformational discoveries from basic research. The invention of the maser and the laser by Charles Townes originated in his research on the temperature of molecules in space, or to put it a different way, about the temperature of the universe. His research contributed to the discovery of that space has a temperature, and that discovery triggered a revolution as cosmology. To measure the feeble signals of molecules in space, Townes invented a new type of molecular signal amplifier called the maser. Townes and his colleagues then extended the maser concept from microwave frequencies to optical frequencies, which led to the invention of the laser. The laser has transformed communications, manufacturing, and lighting that are used in many types of medical procedures. Lasers can be found in essentially every scientific and industrial research laboratory. Applications range from LiDAR systems at the heart of automobile collision avoidance devices to surveying systems that monitor Earth strains and volcanoes and earthquake-prone areas. They are all descended from one scientist's curiosity about the nature of space. Nuclear magnetic resonance, NMR, provided a second example of basic research generating a transformational technology. NMR was invented independently by Felix Bloch at Stanford University and Edward M. Purcell at Harvard University. NMR was invented primarily to study the properties of atomic nuclei, but it quickly became an essential tool for chemists. The major impact of NMR came 25 years after its invention, when powerful computers had become practical. Combining these technologies led to the invention of magnetic resonance imaging, MRI, by Paul Lauterbur and Sir Peter Mansfield in England. MRI makes it possible to take non-invasive pictures anywhere within the human body. It is now a standard imaging technique. I stress these unexpected rewards from basic research because society urgently needs new ways to deal with the ominous threat of climate change. Research on many aspects of energy production and usage is underway, but I want to emphasize the importance of new ideas coming from basic research unrelated to any perceived need. There is no way to predict which area of research will suddenly bloom and possibly create a transformational technology, but the conditions for such discoveries are well known. A research environment in which the search for new knowledge is respected, research is supported, and institutional structures encourages communication and collaboration. Today in the United States, support for basic research is dwindling. Opportunities for a career in basic research are decreasing, and our ability to attract excellent students from home or abroad is declining. Many of my colleagues abroad voice similar concerns. When considered in the context of the most recent report of the Intergovernmental Panel on Climate Change, IPCC, neglect of basic research could be disastrous. It has been known for decades that there is a possibility of a runaway situation in which an increase in global temperature feeds back to accelerate global heating. The process could lead to a massive change in climate and a catastrophic elevation of sea level. The latest report of the IPCC concludes that previous reports erred in being too conservative about the time left before the flow of greenhouse gases is shorter. The time left to stem the flow of greenhouse gases is shorter than had been estimated. We are facing a truly existentialist threat to civilization. New technologies need to be fostered, but in the rush to develop them, a reasonable level of basic research must be maintained if we are to hope for new transformational technologies. The one nation that could provide effective leadership to the world is the United States. Tragically, the current president of the United States is opposed to science and mocks the concept of scientific truth. He and his followers take comfort in the policy of denial. Their policy is guaranteed to make matters worse. I mentioned my title, The Moral Dilemma, and the moral dilemma is simple: how to behave in a situation like that which we face today. I think of that as a subtext for this meeting. Thank you.